Quantum consciousness. Could your mind be a quantum computer? Picture making a decision. Is your choice predetermined, emergent, or the collapse of an underlying quantum wave function? Imagine pausing reality, diving inside a single neuron, and discovering it behaving like a qubit, existing in many states at once. If that were true, could your next thought be the result of quantum superposition collapsing into a decision? Stick around, because by the end of this video, you'll know why Nobel-level physicists argue yes, world-leading neuroscientists argue no, and how new experiments may decide who's right. Neuroscience treats neurons like classical on-off switches, firing electric spikes in complex networks. Quantum physics describes subatomic particles surfing probability waves until measured and collapsing into definite states. Both theories work perfectly until they meet in the brain and produce contradictions when we try to explain subjective experience. If thermal noise ruins quantum states, how could delicate qubits survive inside warm, wet neurons in your skull? Alternatively, could microtubules, hollow protein cylinders, provide shields for quantum coherence? Mathematician Sir Roger Penrose noticed that consciousness seems non-algorithmic, beyond Turing computation, so he teamed up with anesthesiologist Dr. Stuart Hameroff. Their Orchestrated Objective Reduction, Orch-OR model, proposes that microtubules host quantum vibrations that self-collapse intermittently to produce conscious moments. When enough tubules synchronize their quantum states, the wave function collapse resonates across neural assemblies up to 40 times per second, creating the flow of conscious experience. In plain English, your sudden insight or aha moment might be a coordinated quantum bang occurring within the cell scaffolding of your brain. Critics fire back with hard numbers about decoherence and brain temperature. Quantum coherence in a warm brain should vanish in femtoseconds, far quicker than the milliseconds of neuronal firing signals. Physicist Max Tegmark calculated that Penrose's microtubule qubits would decohere 10 to often 10 times faster than biological processes need to exploit them. Even so, some quantum biologists argue that certain subnanoscale structures can protect coherence times long enough for cognitive processing. Beyond microtubules, experiments show quantum behavior in living systems, hinting at nature's uncanny design. Studies of photosynthesis reveal energy transfer in green plants, exploiting quantum superposition to maximize efficiency. Birds navigate via quantum entanglement in cryptochrome proteins, responding to Earth's magnetic field for migration. Human olfaction may detect molecular vibrations via inelastic electron tunneling, suggesting a quantum basis for smell discrimination. Even microtubules isolated in vitro display terahertz-range coherent vibrations under femtosecond spectroscopy. Are these hints that quantum links can persist in biological conditions only we haven't probed yet in living neurons? New instruments like diamond nitrogen vacancy spin sensors can detect single spin flips in room temperature samples. Ultra-fast optical probes capture quantum vibrational modes in proteins with femtosecond resolution. Researchers are applying these tools to live brain tissue slices and organoids to search for quantum signatures. Upcoming experiments couple microwave cavities with biological complexes to test quantum coupling strength in cells. If this quantum mind mystery has you hooked, smash like and hit subscribe so you don't miss the moment science finally captures a thinking qubit. Now let's explore the philosophical stakes of quantum consciousness on free will and identity. If consciousness hinges on quantum collapse, randomness enters cognition, offering a loophole for genuine free will in decision-making. Alternatively, if mind emerges purely from classical complexity, every choice could be deterministic or probabilistic, but devoid of deeper spontaneity. Artificial general intelligence built purely on silicon may remain zombie minds if it lacks biological quantum substrates and collapse events. Philosophers ask, Does Orch-OR revive ancient ideas of a soul embedded in the quantum fabric of space-time geometry? Conversely, if brains are fundamentally classical, consciousness may simply emerge from complex network dynamics and patterns. Either way, understanding mind may illuminate the nature of subjective experience and the hard problem of consciousness. Teams at MIT, Oxford, and the Max Planck Institute are cooling neuronal microtubules to cryogenic temperatures while tracking quantum spin echoes. Persistence of coherence would revolutionize neuroscience. Space-based observatories aim to test quantum gravity's link to consciousness by dropping entangled photons through varying gravitational potentials. Quantum computing simulations attempt to model Orch-OR microtubule networks to predict collapse frequencies and correlates of awareness. Within a decade, we could see decisive data, either dethroning Orch-OR or elevating it to mainstream physics and neuroscience. Whether quantum mechanics is the engine of mind or just a fascinating footnote, the quest unites physics, biology, philosophy, and computer science in unprecedented collaboration. As computational power grows, our ability to simulate and test quantum biological models will expand rapidly. The next thought you have right now could be a classical electrical blip or the collapse of a cosmic probability wave. Either way, the mystery of how matter wakes up remains one of science's greatest frontiers. Will the answer rewrite what it means to be human, or simply deepen our awe at consciousness? Stay curious, share your thoughts in comments, and let's find out together.